Okay, hi everybody. I cannot tell you how unbelievably disturbed I am right now. I think our class, I'm feeling so unsettled. I think so much that I think I'm breaking out in like a mild case of hives. That class today, I think you know what it was. I was just so thrown off by the calculator, and now I've got to go and look at the TI-89 and figure out the keystrokes. But I digress. But boy, I just felt like I just did not have my groove. I did not have my groove today. Oh well, so it goes. Let's go back to your packet. Now again, my packet here, I don't have the letters because I gave mine away, but go back to this question we were doing in class, okay? So we did part A. Let's do part B now, all right? So here, and this is what where you're gonna see just all old content, like old questions coming in the context of the new. The average rate of change of G on the interval from 0 to 3. Average rate of change of G. When you work that out, what do you think it's going to be? The average rate of change of G. It's going to be the slope of the line secant to the G function, which is not graphed, mind you, but the average rate of change of G is going to be G of 3 minus G of 0 all over 3 minus 0. At this point, you're going to have to go and figure out what G of 3 and G of 0 are. You know that G of 3, that was answered right here in part A. G of 3 was this net signed area right in here, and it would be a positive number, mind you, right? Okay. Now, G of 0 is going to be, here's the G function. G of 0 is the definite integral from 2 to 0, and that is going to be this net signed area. However, understand something. When you find G of 3 and G of 0, if it's the net signed area from 2 to 0 of this, that's going to be a negative number. So you're going to have a positive number minus a negative number all divided by 3. Okay, go ahead and find that. And then what I want you to do is go to part D right now. And then part C, it's going to be a little bit, that's a pretty good question, but I want you to go right to part D. Okay, and then replay me for all this particular answers. Okay, so here's part B, the average rate of change of G. And again, notice here's G of 3 and then minus a negative. So my point here is that this number, G of 0, which is the definite integral from 2 to 0, that should be a negative 4. Here is the average rate of change. Part D, find the x-coordinate of each point of inflection of the graph of G. Important point here is you have to look at G double, and remember what's really important is G double has to change sign for there to be a point of inflection. Since you know G double equals F prime, what you can do is look at this graph. This is the graph of F. G double is F prime. You will notice that at x equals 2, look over here, at x equals 2 is a point of non-differentiability of f because G double is f prime. At 4, there's also a corner point, and so is there at 5. So you know that f prime is undefined at 2, 4, and 5, or G double is undefined at 2, 4, and 5. But G double is positive here, G double is negative here, and then G double is positive. So if you look at this, there are points of inflection at x equals 2 and at x equals 5. And if there was a justification, see how it says justify your answer, you would say because G double changes sign at these x values. Okay. All right. Very good. Here's how I want you to go next. And again, because I don't have the letters here, what you're gonna have to do is I want you to go and find this one right here, this question. Go find it in your packet. Okay. Please go find that. Give you a few minutes. And what I want you to do is let's do A, B, and C. All right. A, B, and C. And then replay me for the answers. Read carefully and rejoin me when you are done. Okay, so here's my work. Let's check together. Here I just wrote the function g of x. I know g of 6 will be 5 because if I look at g of 6, this definite integral from 6 to 6, this will just equal 0. So g of 6 is 5. G prime of 6 equals f of 6. And once again, if I take the derivative of g of x, notice here, when I take the derivative with respect to x of g, I'm taking d by dx of this expression. D by dx of this constant will equal 0. And d by dx of this integral will equal just f of x. So g prime of 6 equals f of 6, which equals 3. G double of 6 equals f prime of 6, which equals 0, because look at x equals 6, point of horizontal tangency. Here's part B, g prime equals f. So here is the sign analysis for g prime. Here is where g increases and decreases. I think the question only asked for decreasing. Do not forget, please, intervals of increase and decrease are inclusive by definition only. All right, it's by definition. For the same reason, intervals of concavity are not inclusive just by definition. So I found here g double equals f prime. The critical point for f prime is here at 6. So g double equals 0 at 6 because f prime at 6 equals 0. Okay, and you can see here g double, which is f prime positive, then negative, because the function f is increasing, then decreasing. So the interval where g is concave down is 6 to 15. Okay, question D. Look what we've got here. Trapezoidal approximation. Now make sure that when you are listening to these screencasts that you are taking really good notes. So let's take a look at this. If this is not a midpoint approximation, it's not a right endpoint approximation, this is a trapezoidal approximation. Let's talk about what that means. Well, first, let's just make the subintervals. 6 subintervals of length 3. So that means what I'm going to do here is blow up the picture so you can all do this with me. 6 subintervals. That means we're going to have, let's see, 1 subinterval here, the second one here, 3rd, 4th, 5th, and 6th. Okay? And what I'm going to do is let's just draw some dotted lines down to the function, or up to the function as it were. Okay, and then here. So here's what we're going to do here, everyone, right? Had this been a right endpoint approximation, a right endpoint rectangular approximation, I'll just look at this interval for a second. I would look at this interval, go to the right endpoint, and draw a height here, right? Similarly, if this were a left endpoint approximation, I would go to the left endpoint of this interval right here, go to the height, and make a rectangle. What does it mean to do a trapezoidal approximation? Well, it means instead of drawing rectangles, you draw trapezoids. I'm going to draw one here. What does it mean to be a trapezoid? A trapezoid means I go to this interval and I make a trapezoid. Do you see that? I don't do a rectangle. I go over here and I make this trapezoid. You'll see why I started with the middle subintervals, because if you go over here, this trapezoid, in quotes, ends up being a triangle, okay? And this trapezoid ends up being this triangle. And then similarly here. Okay, so what does it mean to do a trapezoidal approximation? It means that instead of using rectangles, you use trapezoids. And what trapezoids do, and this is where these two intervals are good visuals of it. All you do is you just take this and you connect the endpoints of the interval to create a trapezoid. In the case where one of your kind of bases of the trapezoid is on the x-axis, what you're going to have here is a triangle, which is no big deal. Okay. So the areas of these, now let's take a look at this for a minute. Let's take a look at what it's asking us to do. Approximate, okay, so we have to do this work over here. We have to approximate the definite integral from -3 to 15 of what? Let's see, of f of t dt is approximately equal to what? Using 6 subintervals and using trapezoidal approximations. Well, here's where I'm going to be a little bit more efficient now. From -3 to 15, I'm noticing some symmetry. It's going to work in my favor. I'm working from -3 to 15. So if I head left to right, this net signed area is going to be a negative. This one's going to be a positive, right? But these two areas are going to cancel each other out because negative, positive, it's the same value. Similarly, as I'm heading right, this is a positive net signed area. This is going to be a negative net signed area. So these two values will cancel out. So at the end of the day, to get this approximation, all I need to do is just find the area of these two trapezoids right here, okay? And what I'm going to do here is just find the area of one of them and then double it. What is the area of a trapezoid? Oh, I'm sure you all remember. The area of a trapezoid is base 1 plus base 2, okay? All of that multiplied by height divided by 2. So this definite integral is going to be two of these trapezoids right here. 1 plus 3, okay? All of that times the height, which is 3. This is the height. The height is the distance between a trapezoid's two parallel bases. Times 3, all divided by 2. So this right here is the area of a trapezoid. Area of a trap, in case you forgot, is equal to h over 2 times the quantity b1 plus b2. Height over 2 times base 1 plus base 2. At the end of the day, this definite integral is approximately equal to 12. Okay? And since this question had no context, I believe, it's not like this represents something, right? Nope. This question was strictly using the FTOC part 2. All right? Here's where I want you to go next. Please go to right here, this one. This one right here. And what you're going to do is you're going to do this one and then replay me to check your answers to make sure we're feeling good about things. Okay? On you go. All right, let's see how you did. So part A, here is g of 4, and here is g of negative 2. Interesting point for g of 4. G of 4, you're being asked to find this definite integral. Look at these limits of integration from 1 to 4. So if you look at this graph here from 1 to 4, I'm going from x equals 1 to 4, right? So it's this area right in here. But again, you want to be savvy and advantageous and notice that as I'm heading from left to right, this positive area, right, undoes this negative area. Like these two will add to 0. So really all you need to do is find the area of this remaining trapezoid as a result, okay? The definite integral from 1 to negative 2 for g of negative 2, that's going to require you to go from x equals 1 to x equals negative 2. You know this value is going to be negative because you're heading left and the function's above, right? And so here I just put the negative down so I don't lose it. 1/2 base times height for the area of a triangle, so negative 6, okay? Part B, find instantaneous rate of g with respect to x at x equals 1. That's just saying this, g prime of 1. Since you know g prime equals f, g prime of 1 has to equal f of 1 equals 4. Done. Absolute min of g of x. Great question. Absolute min of g of x. You have to do a g prime sign analysis at the very least. And look what I did here, okay? Here's a g prime sign analysis. I generally first find the critical points or where g prime or f, right? Don't forget g prime just equals f, where f equals 0. And then look at the sign of g prime. So this question is asking for an absolute min. At x equals 3, that's the point at which g has an absolute max. We're looking for an absolute min because the g function, look what's happening. The g function's increasing and then decreasing, right? So the min could be at either endpoint. So you have to compare g of negative 2 versus g of 4 to figure out what the absolute min, and let's go back and look. Find the absolute min value. Be really careful. That means they want to know what the actual y value is. That's the absolute min. When you come down here, you already had the g of negative 2 and the g of 4 values from part A. So we know from part A, g of negative 2 is negative 6 and g of 4 is 2.5. So the absolute min value of g is negative 6, and here's justification. It asked you to justify, didn't it? Let's take a look. It did. Justify your answer. And the justification is the first derivative test for extrema. I used a first derivative test. Okay. Part D was asking for, it says this, the second derivative of g is not defined at x equals 1 and x equals 2, and that is true because g prime, which equals f, means g double equals f prime. So g double is f prime. This is the graph of f here. F prime has a corner point at x equals 1 and a corner point at 2. So it makes sense then that f prime wouldn't exist at 1 and 2. So g double wouldn't exist at 1 and 2. How many of these x values are x coercive points of inflection? We'll take a look at my justification. Here's part D. I did a second derivative sign analysis of g double. G double doesn't exist at x equals 1 and x equals 2, but g double's sign, look what it is, positive, then neg, 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 negative, negative, negative. And I wrote here only x equals 1 as a point of inflection because g double does not change sign at x equals 2. All right, so I have to be really important. The definition of a point of inflection is not a point where g double or the second derivative of the function is equal to 0 or it doesn't exist. An inflection point, by definition, is where the second derivative changes sign, okay? And that is it. So what does that mean about your homework? The homework is to finish this entire packet. So all of it, the whole thing, and I've got it all scrolled down here. Finish the entire packet. What I absolutely must see when you all walk into class on Thursday, which is our long period, I want to see every part of every question on the board, and I will go through it with a very, very picky fine-tooth comb. All right, so that is the fundamental theorem of calculus part 2. And then after we go over homework on Thursday, I will give you the fundamental theorem of calculus part 2, case A. Okay, have a good day off tomorrow. Good luck on the PSATs, and enjoy your day off, seniors, and write those essays.